Do you have a Hantek 20 MHz USB scope model 6022BE? Well, you might find this video of interest, so let's get on with it. Right, I just want to show you one of the issues with the scope. I'm going to have about a 1 volt sine wave, no, 100 millivolts, and can we see it? If we go down the range now, 50 millivolts, there we can see it. Go up, can't really see it now. Go on to the 5 volt range. So if I wind it up, change range, so we get on the 5 volt range, we get a reasonable signal. Now what you can see on the top right is the voltage, the DC voltage that I'm applying to the input of the scope with a sine wave superimposed on it. As you can see on this scope, you can do times 10 and times 1, DC coupled. You cannot, there is no AC coupling, which makes, on like times 1, the scope is rubbish basically. If you wanted to look at the output on a DC coupled amplifier that's got, say, 3 volts on it, this is one of the problems you're going to have. Now if I start raising the voltage on the input, you'll see the trace is going up because it's DC coupled. We keep going up, you can see the voltage climbing. Now soon the trigger needs to shift a bit. Keep going, and at some point there it goes. You'll notice that the signal is starting to clip at the top, and if we keep going up we will just slowly lose the top. And as you can see, we're only at 4 volts DC on the input because it's only a 5 volt DC input, and we get up to like 5 volts, go back down a bit to 5 volts, and the kind of signal is virtually half gone. And if we keep going up, it will disappear altogether and flatten out at 5 volts. And so that's part of the problem, that if you've got a DC bias on your signal, the scope doesn't like it at all. And so what you say is, oh, what if I want to look at something smaller? So let's bring the trigger down again. Say you got something like a, I don't know, 10 millivolt signal. And if I bring the power supply down to 0, or near enough 0, and we increase the gain of the scope, and then we can see it's a little bit noisy, but we've increased the gain. So now we are going to have issues with managing to display it on the scope. So if you're on the 50 millivolt setting on the 5 volt you're on times 1 input, we've effectively gone off the screen at 500 millivolts. So if you want to look at an AC signal that's around 100 millivolts and it's got a DC bias of more than half a volt, you won't be able to see it. You can if you use a times 10 probe, but then you're attenuating everything, so you're altering the impedance as well. But you know, is this really what you would consider a good scope? I couldn't understand it. At first I thought there was an error with the software, that you couldn't remove the DC coupling on the input, and I also thought that when it said that it was 5 volts, the input max was 5 volts, I was assuming that was 5 volts per division. Not if the input DC goes above 5 volts, the scope won't show it. It might have its uses, but I don't know what for. That's part of the issue with this scope, and I think next we'll tear it open and have a look at the insides. I'm going to look at making it an AC coupled scope only, because that I don't care if it's accurate or not. Mainly I just want to be able to display on YouTube graphs like this, and so AC coupled it will have to be, and we'll see if we can do it. So I'd like you to put in the comments below what you think of this scope. Right, I've taken all that away. We'll unplug that. Actually, I might as well turn the scope program off, stop that running, terminate this DVM program, and we'll look at this. I think first of all, you got to get these off, which so I'm getting off screen. Oh, that don't want to come off. Let me find a screwdriver we can jam in there, I think. Want to shift. Ah! Ouch. Oh, I bent my finger now. Alright, so they're off. Oh, sore finger. What does that leave us? Oh, I think that was screwdriver. So, I'm wondering, there's space there. I wonder if I can get two switches and maybe switch the AC coupling. Right. If you look down there, it looks like there's a position for a small fan. Maybe they do one of these that requires a small fan. But there's also some space here, which that doesn't look like it wants to come off. No. It does if you push it. It's reasonably well made. It's got a spring on the back to connect to the back of that, because it's bare metal on the back. So that grounds the bolt or the 0 volts to the back of the box, and then there's a spring on the underneath that grounds to the bottom of the case. All the components are on one side. They can obviously, looking at this, have some other functions on here. Yeah, looks like there's a relay. So let's bring in the microscope camera. Just stick it up there. So let's have a look at some of the components. Can we get in there to have a look? HC4051D. 4051D. You have a HRA, whatever that is. I suppose they're both going to be the same. Another HRA. What's that one? An A7. That's just D2. So what's that? That's it. That's the obviously amplifiers. With a trimmer. Down there. 9093, 990k, 909k. Five one one 0 link. So down there you can just about make out that thin line. That's the input. And so if I want to make this AC coupled, I've got to break that line. What's on the other side? So it doesn't really help there, does it? There's not an easy way of getting to it. One option, depending on how big the hole is that in the past I've sucked the solder out of the joint and found a PTFE sleeve, very thin walled sleeve, that you can push down into the hole and isolate the pin from the hole, and then put a wire on the top and go through another hole with a PTFE wire to carry the connection on. But I doubt if they've made that hole big enough to do that. So we'll turn it back over. And what else have we got here? What is this? That looks like a power supply. Could that be an isolating power supply? Looks like a power supply. We'll have to look it up. Well, you can't see it, can you? Oops. Let's give it a twist. Come on, turn round. I've tightened it up so it doesn't keep flopping about. Well, we'll look at that component later. And we'll pop in. Not sure what's on there. Oh, I don't think they wanted us to know what that one was. So what's this one? CY7C68013A. Is that 804? That can, no, that's B04. But yeah, as to what that one is, we're not going to know. Let's move that to the side. Alright, well this is channel 1, and what I'm going to do is I'm going to attempt to scratch off the solder resist . Let's see if you can actually see that. Trying to do two scopes, use two microscopes. So we're going to scratch away because worst case is I can just solder a link over the broken track and it will be back to being DC coupled. Ouch. Just bear with me, I need a pair of tweezers and I need a capacitor. I'm going to fit 100 nanofarad capacitor as it seems a reasonable value, and I only have that in a 1206, so it's going to be quite big. Let's see how it looks on the board. A bit silly, but I haven't got anything smaller, so what I might do is I could lay it there. And it's not the brilliant idea, but run two wires, because obviously that's going to take up most of that room. But we'll have a go. We'll keep trying. After all, it's only an experiment and it's just for fun. do with a sharper blade, possibly. I need me soldering iron at some point. Where's my capacitor gone? There. Nope, I still can't see it. Where is it? There. Am I still back in frame for you? Something like that. Now I've got to move me again. So what I might try is to stand it up like that. So I still need to take off some more of the paintwork. Right, that's probably enough, and I'm going to cut it somewhere about there. Right, there's the brake. Oh, sorry about it jumping about. Right, get me soldering iron over. Need some solder. Where's my solder gone? Oh, it's over here. It's on the desk already. Some solder. Doesn't help because I have to take my glasses off. I can't see through the microscope with glasses on, and then I can't see anything with the glasses off. Some solder on. So here comes the fun bit. I'm going to stand that on its side. You can't see it at the moment. It's resting against, well, you can just about see it. It's resting against that cap. This is just an experiment. It might not work. No. Hang on a sec. Try putting a blob of solder on the cap. Well, that seems to have held. But is it on the PCB the other side? Oh, I thought I saw some solder flow under there. I think there's a connection. So, if I bring it up, there it goes. There is possibly a connection to the track there, and we'll find out in a minute. Right. Ooh, I need one of these with a camera in. Let's get it out of the way. And now the moment of truth. Does it still work? So hopefully this is the... Oh, we have a red light flashing. We need to start up the scope program, which I've forgotten what it's called or where it is. Oh, it's flashing green now. You probably can't see it, because you can. It's flashing green. Right, that's the scope program. So bring it there. I want a signal, and I need a scope lead, but I don't know where it is. Right, found it. It was on the floor. So I'll put that on there. We'll connect. You can't see that. Signal generator to the ground. And give it a signal. So I don't think it's making connection. So, which is a bit of an issue. Take the scope off. Whoops. Yeah, everything's falling off the desk. This B&C lead's too heavy. Right, let's see if we have a problem. We want to go, if you hear the beep, it's the continuity. Got continuity to there. We have continuity to there. So why am I not seeing a signal? Let's put it into the other one, which we haven't touched. Turn on channel 2, and there we have a signal. So we'll set that down to 2 divisions maybe. Can we get 2 divisions before it squares off? Yep. 2 divisions. And I thought 100 nanofarads would be good enough. But obviously not. Ah! That wasn't good, was it? Have I shorted anything out to ground while I was down there? Let's bring the microscope back in. Might have to move things around. Is there a bridge between... Yeah, look. See that? Alright, let's disconnect power. And maybe I should try and break it with a scalpel. Isn't that amazing? I didn't see that with the other microscope. It's gone now. Okay. Plug it back in. So if we move that, I will do that. Move that up there. That one there. We'll put that one on that line. We'll knock down the signal to 100 millivolts or so, whatever, to 100 millivolt range. So there we have 100 millivolts. And if I stick it into this one, knock it down to 500 millivolts. What have we got? About the same, but with DC offset. So if I do that trick with, we don't need that camera anymore, microscope anymore. If I bring in the resistor again and I connect the resistor, so what I'm doing is I'm going to put a DC bias on it again. If I can find the components I used last time. Ground onto ground. We're putting the resistor in series with a power supply. And we need, where's that capacitor I used last time? There's the resistor into there. Although you can't see this because it's off screen and I'm just holding wires together. But basically what I'm doing is I'm building up that. Everything, all the leads are dangling off my desk and the camera won't scan out right. That's on there. So we've now capacitively coupled the signal into the input. So it may have dropped a bit because it's going through, but now, whoops, if we turn the output on, you can now see that channel 2 is DC coupled, but we're down to about, you know, we can turn it again. We'll turn it up for one grid. That reckons it's about 500 millivolts. So then if we plug this into channel 1, set the trigger up so channel 1's not bouncing around. And we'll see if that is still 1 division, what it is. And now hopefully what I need to do now, I suppose, is I need to put that onto there because I've got to show you this, haven't I? Right, now we can see the DC voltage being injected, actually 1.7 at the moment ish, and if we rise it up 1 volt, I got that connected to the right point. Oh, I got it connected at all, he says. No. Didn't get it connected at all. Right, let's connect it. Alright, so now you can see we have the same settings on the scope, and we've got 0 volts on the input, and we'll whack it up to 1 volt. There you go, over 1 volt, and the sine wave hasn't moved. Put it back down to 0. Get rid of that, that's a pain in the bum. Oops. Put that into there. Trigger it on 2, so it's stationary. And now we'll wind up to 1 volt again. And there's the difference. And so if I was looking at a signal on the output that's not DC coupled with my transistor circuit, and say it had 5 volts on it, well, there you are, 3 volts on the 500 milliohm range, and that's what you see. Now I move it over to channel 1. Look at that. Back, smack bang, either side of the 0 volt setting, doing what you want with a scope. So anyone out there who's got one of these, I recommend to making it more useful for doing what you want to do, like just see a signal and you don't care if it's DC or AC coupled, or you could leave it like this: 1 AC coupled input, 1 DC coupled input. But I shall probably do the same mod to the other side, as it's very rare that I DC couple my scope, because normally I'm looking at AC signals that are biased with DC voltage, so you tend to be on the AC range anyway. I've probably upset the frequency response because of putting that there, but we can have a look at a scope input, and normally they're about, you know, meg input, so we'll just see how it goes with a ×10. But I think I'm going to wrap it up here. Well, no I won't. I'll show you, I'll find some data on a scope input and we'll show you that, and then we'll wrap it up, because I think there's no point you seeing me put it back together. You know, it does what I intended. I'll do the other channel, I think, before I put it back together, and there's no point you all watching that. and I'll show a little circuit of it, how I did the DC bit. But there we go. Right, looking at the scope input, we have the signal coming in here. There's a variable capacitor which I thought at first went to ground, but it doesn't. It seems to go somewhere else. This doesn't appear to be a ground plane there, but it's hard to see because all the wires are, and it could well be that that doesn't go to that ground plane. There might be a track underneath, but the input comes into here, through down to here, through this 900 and effectively 10k, so say 900k, and then it goes on to here, and it goes down to the ground, which is ground this side, through 100k. So effectively 900 plus the 100k. So we're looking at 900, well, we're looking at 1.9 meg input, which is a standard sort of value for a scope input of a 1 meg to ground. And so, you know, it looks like we shall be okay. I've been looking around trying to find a scope input, but you'll effectively find that there is, you know, on a normal scope circuit there will be something like this, and across that capacitor will either be a relay or a switch, because that's like the only real difference between AC coupled and DC coupled. AC coupled you have a capacitor, DC coupled you don't. So that's about it. So if you like what you've seen and you want to, you know, help support my channel, click on the subscribe button. It's free, don't cost anything. Click on the notification bell to get the videos when I release them, and hit that like button. YouTube algorithm likes the like button being hit. Oh, and please comment down below. YouTube also likes the comments, and the more you comment, the more YouTube sees interaction between me and my subscribers. So have a nice day, and I'll catch you on the next one.